Right. Question 9. You've got a solar panel that's 30% efficient and it's plugged into battery that is 90% efficient. Okay. So this one's really easy if you just plug it into the formula. Efficiency 1 times efficiency 2. Make sure you don't write 30. Convert them into decimals. 0.9 equals 0.27. So that's 27%, so the answer is B. But I just want to talk about what's going on in this question and how to think about efficiency. So efficiency is a measurement of how much usable energy do we get out of a system for the amount of energy that's put in. So the amount of energy that's put into a system we can consider to be like 100%. That's all the energy we're putting in. In the case of our solar panel, we only get 30% of that out as usable electricity. So it's 30% efficient, right? If that is being stored by a battery that is only 90% efficient, then you're only storing 90% of that 30%, right? So you need to reduce it. If the battery was worse, if it was a 50% battery, right, we're only going to have 15% efficiency because we're only storing half of our usable or the usable energy that we're getting out of one part of the system. If it was 100% efficient, then we would just have 30% efficiency. Right. Question 10 is just recognizing symbols. Pick the ones you know, compare them to the answer. So, you know, one that I sometimes get dicey with is like variable resistors, which are these ones here, but I know, diodes off by heart. I know cells off by heart, so I just need to look for the answer that has those in the right spots, and that's going to be C. Question 11, and this is a good one. I'll draw this. So we've got some arrangement of batteries. Now, each of these batteries is 12 volts. And let's look at the arrangement, right? So we've got some that are in series. So this battery, these two batteries here, and these two batteries here are in series, which means that there's a current path and it flows through both of them, one after the other. And now the rule is, if you have batteries in series, you add the voltage. So this becomes 24 volts, and this becomes 24 volts. Okay, that seems pretty straightforward. So that's question 11. That's C. All right, 24 volts. It's 24 volt battery, essentially. Question 12. So how many hours? Let's go. Question 12. How many hours would the batteries be likely to last if the arrangement was used to power a device rated at 96 watts? So when we talk about watts, we're talking about power. We look at our formula sheet. We go, is there anything here that looks like it has power in it? Yes, power equals voltage by current. So power equals voltage times current. So what have we got? We know the voltage of our battery. We know the power, we know the watts, and we know that these batteries can provide 4 amp hours each. But let's just stop for a second because we need to think about what happens to these batteries when they're in parallel. So if we look at this, there's actually 2 current paths here through this arrangement of batteries, and they're in parallel with each other. So they join back up. Now, when something's in parallel, you add the current. So series add the voltage, parallel add the current. So what we really have here, rather than these being 4 amp hour, we have a total of 8 amp hours. And we're going to need that later. But for the time being, we know the watts and we know the voltage. We know how much current can be supplied per hour. That's 8 amps per hour. But we don't know how much current our device is actually going to be drawing. So we need to figure out current. So we need to do some rearranging to get current on its own. Current equals power over voltage, which equals 96 divided by 24 which equals 4 amps. So we're drawing 4 amps. This battery can supply 8 amps per hour. So if it can supply 8 amps per hour, it can supply 4 amps for 2 hours. So that's our answer, 2 hours. So that's B. Right, let's get rid of that. Question 13, an OH&S question. What do we got? The main role of occupational health and safety guidelines in a workshop is to provide instructions, protective rules, so recommendations to all users. So in the workshop, specifically this question asks in the workshop. Now, here's rules for users of the workshop. Instructions for the operation of all equipment, yeah, sometimes, but there's other, pieces of documentation that do that as well. Rules for the protection of the teacher, well, no, they're for everybody, not just for the teacher. Recommendations to all users, I mean, that's not bad, but this one mentions the workshop, so that question makes the most sense if it is rules for the workshop. Cool. Question 14. Fire extinguishers used to put out electrical fires work by removing, all right, what's a fire need? Oxygen. Do all fires need oxygen? Tick. Do all fires need hydrogen? No. Do all fires need carbon dioxide? No. Do all fires need carbon monoxide? No. The answer is A. All fires need oxygen. Therefore, the fire extinguishers must work by removing oxygen. Question 15 is resistors in parallel. So, resistors in parallel. The formula is 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. So that equals 1 over 12 plus 1 over 12 plus 1 over 12, which is equal to 3 over 12. Now, important step. We don't want to know what 1 over RT or the total resistance is. We don't want 1 over resistance total. The question asks us for the total resistance. So can we flip these? We can. So this becomes, just run out of room, resistance total over 1 equals 12 over 3. What's 12 divided by 3? It's 4. So the resistance total equals 4. And anything divided by 1 is just itself, right? 1 by 1 is itself, 2 by 1 is 2, 3 by 1. So we just have resistance total. So it's 4. It's 4 ohms. So the answer for question 15 is B. File. New. Don't save. Question 16. Okay, we've got a pulley. It's got a mass. So diagram above shows a pulley system, 6 kilo mass. Ignoring the mass of the lower pulley and taking the gravitational constant to be 10 meters per second, the minimum force needed to keep the 6 kilogram mass in equilibrium is. Okay, so think to yourself, well, these are all in newtons, so it might be nice to know what our load is here. Our load is our mass here. What that is in newtons. So force equals mass times acceleration. Our mass is 6 kilos. They already gave us our gravitational constant. So our force is 60 newtons. Now, this is a pulley. My sort of shorthand rule for figuring out the mechanical advantage of pulleys, so that's like how much force multiplication you get, I guess you can think of it as force multiplication, is to just count the number of rungs between, or the rope between the pulleys, not counting the bit that you would pull. So my mechanical advantage here is going to be 1, 2, 2 to 1, which means that it's going to take me half as much force here as is hanging off this pulley. So it's going to be 30 newtons. So the answer for this one is C. It's really worth looking at pulleys and mechanical advantage. Just have a crack at some of the questions out of your book, just to get that into your head again. Question 17. Hacksaw be used safely and accurately when cutting thick metal rod. Okay, so think about this, right? Hold the hacksaw with one hand and the rod with the other hand. I mean, no. Why would you do that? It's a terrible idea. Apply pressure only on the forward stroke and clamp the rod. I mean, those both sound like good suggestions. The teeth of a hacksaw are, or should be, angled that way, so that when you push, they're cutting, and when you pull, they're not cutting. And I like the clamping. That makes sense to me. Make sure the teeth face the handle. I mean, we just said that that's wrong, but even if you didn't know that was wrong, this one sounds great because there's clamp in there and cut in an upward direction. I mean, what does that mean? Does that mean you have to stand underneath the thick metal rod so that you can cut in an upward direction? That's a person, by the way. That sounds like a terrible idea. Ooh. Question 18. All right, I like this question too. The wheel. So the wheel shown above has 200 Newton meters of torque, and it's got a 40 centimeter diameter. If we assume full contact and no slippage, the force of the wheel on the road is, okay, so we know the torque. We don't know the force. We do know the diameter of the wheel. Let's just, what do we got? We got anything that helps us do that? Well, look at that. Torque equals force times distance. Torque equals force times distance. And you know what? I'll just draw our wheel. So where is our torque? Well, it's a wheel, right? So we assume that given that the wheel is being driven, that there is some sort of axle in the middle. And we know that the torque is equal to 200 Newton meters. We also know that here's our road, and we want to know what's the force here at our road surface. And we also need to know the distance. Now, they've been a little bit sneaky here because they gave us this 40 centimeters. But if we use 40 centimeters, we'll actually get the wrong answer because the distance from, where our torque is being applied and the surface of our road is only half of this distance. So our distance is actually only 20 centimeters. So we know we only have one unknown, which is force, right? So we need to rearrange our equation to get a force on its own. So torque equals force times distance. What are we doing again? We're trying to find force. So distance. So now we can rearrange that as force equals torque divided by distance. So, and I've run out of room. So our torque is 200 Newton meters. Our distance is 20. Be mindful, working in meters because it's Newton meters and this is centimeters. So that would actually be 200 divided by 0.2. Plug that into our calculator. Equals 1,000. So the answer is 1,000 newtons force. And I just need to check. I just want to double check that. That's question 18. Cool. All right. And many students use the diameter and not the radius in the calculations. By the way, all of the VCAR exams that you can find on the VCAR website, you can just Google VCAR systems exams or VCAR any subject you're doing in Year 12 exams, has the examiner's report, answers and common mistakes of students. They're really, really valuable as a resource. All right, now that I've proved to myself I can do simple torque questions, we'll move on. Question 19. A speed of 2.592 meters per second expressed to two significant figures is, right, we need to revisit this in some revision, I know that, but let's just think two significant figures. So significant figures, we'll go through this in class, are figures that tell you about the accuracy of your measurement. And if you want to express it as two significant figures, well, there's two options here that have only two figures. So they're a good place to start, right? Now, why you would pick 2.6 over 2.5 is because if you're going to express something in a different way, you need to round it, right? So this expressed as two significant figures becomes 2.6. And last multiple choice question. Question 20. So the gear ratio of the compound gear train shown above is, okay, so the formula for gear ratios is teeth on driven, teeth on divided by teeth on driver. Right, so teeth on driven of this first combination, 16 divided by 8, that's 2 over 1. Of the second combination, that's 40 divided by 8, that's 5 over 1. All right, if you multiply those together, you get 10 over 1. And if you express that as a ratio, there's 10 of something to 1 of something else. So it's 10 to 1. So the answer is D. All right, that's the multiple choice. I'll make another video on the short answers pretty soon.